Good afternoon, everyone. I know we're running a little bit behind schedule, and we've just been given some instructions to try to do some fast forwards, but we don't want to shortchange, I think, the rich content that is going to be part of this session. So we're going to dispense with introductions. I am Dan Arvizu. I'm the director at the National Renewable Energy Laboratory. I have another part-time, I call full-time job, which is the chairman of the National Science Board, which gives me a unique perspective on things that the U.S. government is investing in. And I get the opportunity to talk a little bit about clean energy. So we've heard a lot about, I think, our major developments in oil and gas and the real opportunity that it presents. This session really is more about how does the long-term energy system look, and where and what role does clean energy play in that. I hope what you'll take away is that there's not as much conflict as some people would like to think there is, and that there's a lot of opportunity for there to be great synergism. So without further ado, let me jump into this. Again, I've got a presentation that was developed for a little bit longer time schedule than what I actually have, so I'm going to fast forward through a few of these. I do want to start with kind of some broad context, and this context really is some things that I think maybe is obvious to some of you, but maybe not all of you. One is the renewable energy industry is growing quite dramatically, and there's been over $2 trillion of investment globally, and it continues to grow at double-digit rates. The real question has to do with, is that sustainable? What does that mean long term? And ultimately, what role will it play in the energy mix of the energy system of the future? Public policy, and we heard some of this morning, has driven this energy sector. More generally, for the last 100 years, certainly public policy for clean energy has been driving much of what we've seen in terms of progress. I think that's a good thing. It's global public policy. So I think one would, if you want to just kind of put a fine point on it, Germany made some huge investments, tens of billions of dollars with their feed-in tariff to create a market. China made a similar huge investment of hundreds of billions of dollars to scale up manufacturing. And we now have the benefits of that. I would start that the U.S. invested in innovation early on, but much of what actually is out there has been driven by public policy, certainly in the clean energy space. Conventional, non-conventional gas and oil has certainly changed the focus of more recent developments in energy that we've heard about a lot about that. And we also heard this morning that the infrastructure investments will be made. In the OECD, the more developed nations, that infrastructure investment is typically about replacing aging infrastructure. In the developing nations, that's really about new infrastructure. And there's a bit of a challenge there in terms of what to invest in. And so hopefully what you'll get out of this talk is that we have a choice. We're going to make investments in infrastructure. The choice is on what and to what end. And I think that really will hopefully help focus the discussion. The last key point I want to make is one that I live with and I find to be the most exciting one. And that is that new technology is creating a platform for disruptive events, not just on technology, but on business models, and not just in the energy sector. It's happening in financial services. It's happening in healthcare. I sit on a board of a major insurance company, and in the boardroom, we discuss the changing nature of commodities. It's really interesting to hear insurance people talk about things like differentiation, option value of products, and things like disintermediation, which is a term I heard first in energy, but now you're hearing it in other sectors of our economy as well. All very important in terms of where we're going next. Here's the bottom line. We need to make an energy transformation from where we are today, which is the left-hand side of this chart, to where we need to be in the future, which is the right-hand side of this chart. And this is the attributes of an energy system that we aspire to. It's not the one we have today, but it's the one that we aspire to. And as a technologist, it kind of pains me to say this, but one of the things I would say is we need to be technology agnostic. Any technology that can achieve the attributes that you see on the right-hand side is technologies to be applauded. And so this really is a form of market, information and discipline that allows us to aspire to these attributes. Now, different technologies will have different challenges. The last bullet on here is more consumer-driven choice, and I think that hopefully resonates with everybody. Anyway,
This is the kind of where we need to go. I think that's really important. You've seen these charts. I'm not going to belabor them too much, but in the U.S., the energy consumption is relatively flat, has been for some time. There's great demand increase in emerging economies, but not in the developed nations. And on the right-hand side of this chart, what you see is kind of a mix, and we've heard this now several different times this morning. What we're seeing in terms of year-by-year change of that energy mix, we're seeing that renewables and natural gas is displacing coal. Now, that also is giving rise to reductions in greenhouse gas emissions, which I think is an important piece of our future energy system that we need to not lose sight of as we exploit all these new opportunities. In terms of the energy mix relative to renewables, this is what we get in terms of the upper graphic there is capacity, and I give lots of talks, and I always get a question about, well, you talk about capacity, but you really ought to talk about generation. How many kilowatt hours did we actually generate? That's the bottom graph. I want to make sure that people understand that. And so 13% of our electricity energy comes from renewable energy. Okay? About half of that is hydro, about half of that is non-hydro renewables. 4% out of wind, 1% out of solar. These are incredibly, I think, impressive numbers from those of us who have watched these technologies grow from essentially nothing to where we are today. There continues to be investment, even in this sector. This is global investment. This is the $2 trillion that I mentioned earlier. And the good news is in 2014, we finally saw back an uptick in terms of how much investment's being made. On the left-hand side of this graph, what you see is where the investments are being made. So the red is Asia Pacific, the blue is Europe, Middle East, and the green is the blue is North America, and the green is Europe, Middle East. What you see is much bigger investments these days in primarily China and Japan, and lesser so in Europe. And the U.S. is starting to tick back up. The right-hand side of this graph and the histogram that you see there is on what technologies are we spending money. So that investment is primarily, the blue is wind and the yellow is solar. So you can see that the investment over the last few years has primarily been dominated by solar technologies, and we heard a little bit about that also today. Another key element of what we are working on and in our laboratory at the National Renewable Lab is this notion of what's possible. What can you actually get? I used to be in front of Congress all the time, and I used to try to answer the questions, how much, when is it real and how much can you get? Was kind of the two questions I used to get. This study that was done now several years ago, many stakeholders, I won't go into it, you can look it up on the web, it's called the Renewable Energy Futures Study, is actually an analysis that says what's possible. And we actually did an hour-by-hour simulation of the load in 2050 and asked ourselves the questions, can you do 20% renewables? Can you do 30, 40, 50? We went all the way up to 90%. And we kind of focused on 80%. Our conclusion was you actually can do 80% of the energy demand on an hour-by-hour basis in the year 2050 in this country from renewable energy. Some modest changes in transmission, some other things, but it can be done. This is not a prediction or a projection. It is simply an analysis that says what's possible, okay? So we've done this study, by the way, in many other countries, and the results are always the same. There's plenty of potential, and there's plenty of technical and economic potential. That is not the question that's in front of us. The question in front of us is how do you do it? And what is the right mix for this? And we took a very central station-centric look at it, and I will offer that in different regions of the world and in different regions of this country, there's going to be a mix of distributed generation and central station that will be different for different regions of the world and of this country. And that is to be determined as time goes on. There's a bunch of factors that will determine how much of each of those we will have. But what we're doing in terms of analysis and study is to try to figure out what does it take to do that? What are the technical barriers? What are the business model changes that need to occur? And how does that affect both our R&D agenda and our public policy agenda as well? So I'll go on and just say, look, if you want to take away one slide from this talk, this is it. There's still a lot of room for new innovation and new opportunity to fund, I think, the investments that are going to fashion the future. We need to accelerate technology adoption. We need to integrate technologies at scale. The technologies that got us to where we are today are not the technologies that are going to take us from the 1% solar or 4% wind to the 10 or 20% solar, 30 or 40% wind that's possible. These technologies will be very different. And so we've got a lot to do, and we got to do it. We can do it in collaboration. This is the place where I would go through a lot of technologies talk. I won't do that in the interest of time. In the U.S., just recognize, I'm going to talk about a couple of technologies very quickly. One is solar. 20 gigawatts, it's amazing that's how much deployment we have in this country. 200 gigawatts globally. Costs are coming down, and we're going to be near parity with conventional energy generation very, very shortly, both on the utility side as well as on the retail side. Where are those modules being manufactured? Well, they're being manufactured in Asia. This is the left-hand graphic here. 64% come from China. So these are technologies that we pioneered. These are technologies that we developed in this country in the late 80s and early 90s. I was part of that whole process. We are now buying most of that technology from other countries. There's manufacturers and some other things. The question that's in front of us is, can we do better than that? Can we harvest the investments that we've made in innovation in this country for U.S. benefit? That's a big question that I get in front of Congress all the time. Here's a potpourri of some of the technologies that we're pursuing, and I'm going to call this next-gen technology. And these are technologies that will give us the opportunity to regain our manufacturing prowess, create jobs in this country, and to really regain the supply chain that is really part of the ecosystem on all these technologies. I serve on the National Science Board. In fact, I chair the Science Board these days. And one of the things that I find interesting is that there is no shortage of innovation and great ideas. So even in the Science Foundation, where we spend $7.5 billion of your well-earned tax dollars on science and innovation, we roll up. How much of that is really relevant to clean energy? Well, the number for last year was $377 million. And so I picked out a couple of examples of some really interesting, what I'm calling forward-looking, next generation technologies from the Science Foundation. The thing you see on the left is a transparent photovoltaic device that might be part of a building integrated design in the future. These technologies are happening across the nation in our universities. So it's not just confined to what the Department of Energy funds. It is really ubiquitous, and there is incredible interest from our younger generation and from university students. Every university that I've been to in recent years has an energy club, has incredible enthusiasm in this area. We have only begun to tap the intellectual capacity and potential of what I think is the next generation. We're at the very beginning of a very, very fast-growing, I think, opportunity in terms of energy mix. Wind, we heard a little bit about that. We have 66 gigawatts in this country today, 370 globally. These are massive machines, primarily central station. And I do agree with the idea that we're going to probably go into the offshore arena next. That's the next big thing that'll happen in wind. I'm not supposed to talk about policy because I'm a technologist and we're supposed to be technology agnostic or policy agnostic. But I got to tell you that independent of what happens in Washington, these things are going to go. And they're going to go because there's a compelling value proposition. China is still the leader in some of the renewable deployments. But there is tremendous opportunity for new innovation. We're looking at carbon composite, new blades, and new ways of generating energy at a much, much lower cost. And again, the floating platforms offshore is a big, big deal. I do want to say some things about analysis, because analysis is so important. Two enabling competencies in our research community that have really changed the game. One is high-performance computing, and the other is analysis. And I'll just give you a little bit of a detail on this particular graphic. We started with techno-economic analysis, and the upper left-hand chart is a flow diagram of how you would essentially manufacture lithium-ion batteries. And it's got all the process steps, and it tells you how much each one of them is going to cost. And you start from kind of basic material costs and work up what is the techno-economic potential for that. Then we started looking at global supply chain. It's not just about the widget that you build or the technology idea. It's much broader than that. And then we talked about this whole notion of region by region comparison. What is the effect of low-cost labor and those kinds of things? And then we went to technology by technology. New technology, next generation technology. What are the potentials for these in terms of cost and economics? And then ultimately, on the right-hand bottom of this graphic, we're looking at sensitivity analysis. What factors make a difference in terms of how these technologies get deployed, get manufactured, how many jobs they create, where they create them? And this analysis capability does two things. It informs our R&D agenda, and it informs decision processes for investors. And that really is the bottom line for, I think, having a government role that makes a difference, set the framework, and let the markets work in a way that really gives you tremendous opportunity. So systems integration is the next big thing. So we've got this, we've got the starter kit, we've got technology, it's in the marketplace. We're not scared anymore that the grid's going to fail because we put too much on. But we do have to pay attention. The grid is not designed for distributed, variable generation. It's designed for variable loads. We can deal with that, but variable generation is not so easy. And where these two meet is really, really important. So we're working on this. This is another kind of a summary slide that's got the graphics regarding what are the important points that are going to be made. There is lots of things that need to be done, and we need to be cautious, and we need to de-risk the technology going forward. We've got a new initiative that the Secretary of Energy has just announced. It's part of the FY16 budget. It was on the Hill 2 days ago, essentially providing the information to the appropriators regarding why this is important. And in fact, we have about $200 million in the Department of Energy spent on grid modernization. Here are the technical pillars of things that we're working on. Lots of opportunities. 17 national labs are part of this thing. We're requesting another $156 million of plus up in a budget we know is going to be very challenged, but it's really important to continue to prioritize and put money into these things. This is the way in which we will, as a country, develop that next generation energy system that allows us to accommodate these variable generations and variable loads at the same time and squeeze the inefficiency out of the system that we have, which is incredibly inefficient and unintelligent and not reliable in many different ways. The last thing I'll say is, and I was going to make a little bit longer pitch on this, but this has to do with some projects that we have going on in our energy systems integration facility. But typically the solar community and the utilities tend to be at odds, and in Hawaii you've got small grids, and you've got very much interest in. They got high energy prices and a lot of interest in putting on rooftop solar. And we had a problem that the utility said, if you have more capacity on a distribution feeder than 120% of the minimum daily load, we are not going to let you connect any more solar onto the grid because it's going to cause bad things to happen, which is actually true. Solar City, in this case, was saying, we're at an impasse. We think we can do better than this. The real key happened to be next generation smart inverters. And we were able to test those inverters, demonstrate that you can actually, with this new technology, put it onto these rooftop solar programs, you can actually mitigate that problem dramatically. And it really broke the logjam in the Hawaii area. Just one little case, an example of things that really I think are happening to demonstrate that we're on the right track. Final slide, invest in innovation. We are just at the beginning of what's going to be ultimately a very, very exciting area. Invent the future we want. We can continue to reinvest in the infrastructure that we've had of the past. That would not be my counsel. We need to invest in the infrastructure of the future that will take us to the next level, that will do the things that we need it to do in this century. Access to capital is huge. It's private sector capital. We've got to de-risk the technology. That's the role for government. Partner on a global scale. Go to nrel.gov. You can get a copy of these slides. Thank you. And now Sally.
Okay, well, thank you, Dan, very much for that whirlwind tour of clean energy. That was a fantastic introduction to this discussion. The way we're going to run this is we'll have a conversation for about 25 minutes, and in the last 5 to 7 minutes or so, we'll take questions. So if you could pass the cards, that would be great. Okay, so we're talking about technology. Later you're going to hear about policy, finance, and markets, and so forth. Okay, I just have to introduce who's here because we have an amazing panel. Dan Arvizu, he's the director of the National Renewable Energy Lab. You've heard him talk. We also have Terry Boston here. He's the CEO of the PJM Interconnection. This is the largest power grid in North America. We have Steve Corneli, who's the NRG Senior Vice President for Policy and Strategy. NRG is known as being one of the most progressive power companies embracing clean energy technology with very creative business models. And finally, Arun Majumdar, who's the J. Precourt Professor at Stanford University in Mechanical Engineering. formerly at Google, and formerly the inaugural director of ARPA-E, the highly acclaimed energy technology program that spurred so much innovation. So thank you for participating. So let's get right into this. So I'd like to start with you, Terry. That could you tell us some of the changes? You're on the ground there. You're operating a grid. Tell us about the changes that are taking place.
Yeah, it is an exciting time. As a matter of fact, when Arun called me to ask me to sit on the panel, I quickly said yes, because being the CEO of an RTO is a lot like being the groundskeeper at a graveyard. You're over a lot of people. You're just not sure if anybody's listening. So believe it or not, we cleared $50 billion through our market. The single biggest change that we've had technology-wise came from this morning's presentation, the hydraulic fracturing and the Marcellus Shale. I walked into the office the coldest day, being forecasted on January 8th of this year. On January 5th, the Marcellus Shale opened at 67 cents per million BTUs. And if you multiply that times a 6,000 BTU natural gas combined cycle plant, which is all that we've cleared in our market in the last 4 years, you end up with $4 per megawatt hour fuel cost, which is half that of the nuclear fuel cost, and 1/5 of the capital cost of a nuclear plant. So Marcellus Shale has changed our world. There's at least 3 manufacturers now that are pushing 60% efficiency, and the world belongs to the efficiency on the Marcellus Shale. Second is happening in terms of technology, more worldwide than it is in the U.S., and that's high voltage DC. If you look at the rest of the world, Europe, with the focus on renewables, and China with the focus on everything, and the growth they've had in energy, 20% of that new grid is HVDC. Thomas Edison was right. Westinghouse was wrong. If you want controllability, if you want long-haul transport for renewables, HVDC is the right answer. And what has made that available is the voltage source converter and the improvement in power electronics. As a matter of fact, those improvements are growing very rapidly. I've worked on a project that uses diamond-based thyristors, which could be 2 orders of magnitude more throughput. So to Dan's comment about smart inverters, and we did not coordinate this, we require, on a filing that we made 2 weeks ago at FERC, that if you're going to hook to the PJM grid, that you have to have one of the smart inverters that Dan talked about that can automatically do voltage and frequency control of the grid, so it becomes self-healing as you go forth. And the last one on my list, and I actually started my career there, I wrote my graduate thesis on the optimization of a 1,700 megawatt pump storage plant, is storage. Since I bought my Chevy Volt, which was the 11th one off the assembly line, Secretary Chu informed me 2 weeks ago that battery technology is approved by 80%. We have about 100 megawatts of batteries already connected through Pay for Performance. This morning I mentioned we provide the market draw for technology. By putting in Pay for Performance, where we say we will only pay you if you respond to the signal I send you, and we measure it in milliseconds in many cases. We can actually control cars, batteries that are used to deaccelerate trains, and make them fungible in our market. So those are the ones that I see that are moving. And I noticed earlier in our question we said Thomas Edison would identify a substation if he walked into today in the equipment. I strongly disagree with that, because if you look at the power electronics, you look at 3,000 servers that we use to control the power grid. This is not your father's Oldsmobile. They don't even make your father's Oldsmobile anymore. So.
Okay, great. Yeah, well, thanks, Steve. Let's switch to you. So from a power producer point of view, what are the technologies that have you excited? What's making your business profitable and your life easier?
Yeah, actually, most of these innovations, this is kind of, I don't know if it's a dirty little secret, but it's a unique thing about the U.S. power industry, that most of the innovations that Dan talked about and that we've all been talking about, that Terry's talking about, actually make most people who own assets in the power business's life miserable. These are all disruptive technologies, even, starting with the fracking revolution, which is a great thing for our economy and our country, clearly. But in the power markets, as Terry pointed out, when you have power markets, the price is set by the highest bidder for everybody. It's sort of like, whoever wins on eBay, everybody gets paid that amount, and which is sort of how corn markets and other markets work too. So when the price of gas is really low, and you get $4 or outside where there's pipeline transport and the gas isn't trapped inside the Marcellus zone, you get $20 power prices. That's what everybody gets paid, unless there's extremely high amounts of demand, which of course are falling because of disruptive innovation and efficiency and structural changes in our economy. LED light bulbs, can knock out 80% of the load of a building that has efficient fluorescent bulbs in it. So from a power provider sense, and I think from our cousins in the regulated utility business, NRG's a competitive power company, but the people who own the transmission lines and the distribution systems, we're seeing lower prices and decreased throughput as people conserve more energy, make it at home, generate it at home, store it at home, and use less of it at home. And the stuff that they are buying from the grid has a much lower price, primarily because of the revolution in our primary marginal fuel in this country. So there's nothing in that really makes us more money or makes us happier. But there are some very exciting things in the business and things that we're embracing as a company precisely because we feel a mandate and a compelling mandate to grow. And we see huge opportunities to grow through some technologies and business models. So let me just run down sort of the list. Given this rather depressing environment, we focus on things that actually, we look for things that are, they have cost synergies, like they not only are cheaper, but they combine multiple products with one set of costs. They're customer facing because as the wholesale grid gets cheaper and cheaper, more and more the value is shifting to the way customers use their energy, the kind of energy they want. Customers they want to be connected when next time they want their own power next time Hurricane Sandy comes through. They want cleaner power. Many of the Fortune 500 companies are making declarations that they're going to be 100% renewable powered by 2020 or 2030. Huge market opportunities there. Consumers are increasingly interested in rooftop solar, electric vehicle charging systems. All of those things are big growth opportunities for us. But the real answer, the thing that we're really excited about, is not any given technology, but it's a new business model. And the business model that is really exciting is thinking about bundling together several of these things for residential consumers, business consumers, C&I consumers, and having them all have smart technologies inside. I'll say smart inverters to be the third person to say it. Smart thermostats, smart electric vehicle charging systems, smart control systems that not only save the customer money, but they also help solve the voltage problems, the anti-islanding problems, the power quality problems, not just for the customer, but for the local utility. And if aggregated into big enough chunks, they help Terry keep the lights on and make sure the grid is in balance and efficient. So that's a great business model because we can do, with the same stuff and the same cost centers, the same innovative disruptive technology, we can create customer value. We can create additional value for the local utility, both in terms of keeping their system running and helping them avoid costs that would otherwise be stranded, like new substations that they might not really need. And then we can create value for the grid. And, that sounds like a pretty good deal when you can make three kinds of value with one kind of cost. So we get excited about that kind of stuff.
Yeah, thanks for describing that. There's a fantastic app. It's called ISO Today. And it shows how much renewable power we have on the grid every day in the California system. And last week I was looking at it, and we had 7 gigawatts of renewable energy. Most of that, about 80%, was solar. So Arun, what's happened to? And that's 25% of our grid power at the middle of the day is renewable energy, and again, a good fraction of it solar. How did all that happen? What are the key innovations that's made that possible?
First of all, let me just start by saying that Dave Danielson could not be here. And he is in Washington in EER, Office of Energy Efficient Renewable Energy. And let me just say that he's doing a fantastic job in trying to run the ship out there and really focus on clean energy in a variety of ways. As you said, I had the opportunity to be the director of ARPA-E. And what I saw in the ideas that were being put forward from this science and engineering and innovation infrastructure that we have in the United States is absolutely staggering. There's so many ideas, and that's the good news. The bad news is that we didn't have enough money to support all of them. We don't want to support all of them, but there are some really good ideas that we could not support. And I think that was one of the systemic issues that we really need to address. And frankly, I hope they increase ARPA's budget and just double it. Having said that, you asked me about why did this happen. I think there are two primary things. One is that it's just cheaper. The cost has come down, for example, for wind or for solar. It's come down at a rate that a lot of us did not predict. Like in 2010, we started something called the Sunshot Initiative to reduce the cost of electricity production from electricity generation from solar to 5 cents a kilowatt hour without subsidies. And what we are hearing now is that they're going to reach it before the end of this decade. It was a 2020 goal. It's going to happen before the end of the decade. And now when you have cost parity in terms of, and not just cost parity, actually lower cost, it's just cheaper. The other is many of the states, as you know, have asked for cleaner mixes of energy through things like renewable portfolio standards, et cetera. And the ISOs, the grid operators out there, are trying to meet those goals. And thereby, you find that a lot of solar and wind has been integrated into the grid. The big challenge is in the future. So looking ahead in 5, 10 years, the cost can come down even more. There's plenty of headroom in solar for the efficiency to go up, for the weight to be reduced, and solar cost to be further reduced. Then you ask the question, where's the barrier? And the barrier really comes in the integration of that because, as we heard, it is intermittent, fine. The other part is decentralized, and our grid, as was talked about, is really the architecture of the grid goes back to Tesla and Edison. And that's, in fact, the architecture is something that the Edison would recognize, maybe not the devices. And that architecture was built for centralized generation with, if there's anything distributed, was the load. And the generation always followed the load. That means if you flip the light switch, then there's somewhere that the generator had to go up, right? That will have to change because with intermittency, the load may have to follow the generation. And so I think that's something, a fundamental change that will have to happen if you are to integrate higher penetrations of the grid, and thereby communication, networking. Tesla and Edison never had solar power, solar photovoltaics. They never had power electronics, as was talked about. They never had networking or distributed computing that we have today. And if you mix all that, you find that you have to think about the grid in a fundamentally different way and still be able to be compatible with today's grid. Then the question comes in, okay, if you do all that, what about security? And this man knows a lot about that. And I think that is something distributed energy can actually help in that because it gives you resilience in terms of when somehow someone hacks into this. And I'll just stop at that, but there's tremendous headroom for technology innovations to come in, but we got to think about the system as a whole as opposed to just the components.
Maybe you want to speak to this,
To the point, I started my career writing economic dispatch software so that we could chase the load, the generators, the load variation, so there's nothing worse than a steel mill, perhaps a windmill. But we are now capable with the smarts that we have. In Steve's case, we have the first commercial fleet of plug-in hybrid vehicles. If we had 300,000 of those on the PJM system, we would be able to handle the regulation for all of the wind that occurred. If you think about if we had 2% of the cars in PJM, if they were plug-in hybrid vehicles under our control, it would be more than the 5,400 megawatts of pump storage that we had. If we had half of the water heaters in this country converted to be grid control storage water heaters, which France has already done, that would be the equivalent to all of the pump storage, 24 gigawatts of pump storage that we have. So if we use the load to chase the variable generation, it will solve many of the problems that we have on the intermittency.
And create business opportunities for people who can go in and figure out the best way to continue to give people, like Amory Lovin says, you know, they don't want electricity, they want cold beer and hot showers. Here's a colder beer, a hotter shower, and when you're not using it, or we can use it smarter so that we can get those solutions to the grid rather than having to, you know, we can have load adapt to intermittent generation as well as have controllable generation adapt to inelastic loads.
I want to switch. We've talked about, clean natural gas. We've talked about clean, wind and solar power. But there's another option too, and actually, energy is a pioneer in this, and that's the topic of carbon capture and storage. So by 2016, you plan to be capturing 1.6 million tons of CO2 from a coal-fired power plant, and then you're going to pump it underground to enhance oil recovery. Can you tell us more about this technology, this project, how it's going? Do you think it's going to scale?
Yeah, well, it is really exciting. And just a little background, I spent a lot of time in Washington in the mid-2000s where there were lots of discussions about climate change, technology, energy policy. What would it take to actually reduce CO2 emissions, and what was the government's role in that? And one of the things that two things became really clear in that. One was that CCS, especially the ability to put it on the back end of existing coal plants, was really important, not only in the US where you have a lot of existing coal plants, but especially in China and other developing parts of the country where there were new coal plants being built at the tune of multiple ones every week. And there's still lots of coal plants being built in China. And they're all the sort of thing, if you want to really take care of the CO2, you've either got to shut them down or put this stuff on the back. So that was one thing that became very clear. The other was that everybody seemed to say the magic number was it's going to take a carbon price of $90 a ton to pay for that stuff. And having spent a lot of time in Washington dealing with carbon and climate issues, I can tell you $90 a ton is not something that is in the realm of, like what anybody thinks is feasible politically. $1 a ton may not be feasible politically, but 90 definitely isn't. So the key thing about this technology, two key things about what we're doing is A, it goes on the back of an existing coal plant, and two, it takes the CO2 and incorporates it into a sort of joint venture project that owns the oil field where it's used for enhanced oil recovery. And the great thing about that is oil, sort of on average over time, although recently it's gotten kind of soft, but it is worth quite a bit of money per barrel. And CO2 in a field that you've pumped all that you can suck out of the pore space with the natural pressure and the viscosity of the oil down there, it's got about half the oil that's down there still left. And you put CO2 in there, and it pressurizes and it lubricates it, and you get a whole bunch more CO2 out. Sometimes the rule of thumb of 1 to 3 barrels per ton of CO2. Well, even at $50 a barrel, that's $150 per ton. Well, that's more than 90. So you don't need a carbon price if you can A, find the technology that really works, and B, find a way to have the business model that integrates it in with the oil production, and C, have some way to, like everybody in the oil business has to hedge volatility. So we're very excited about that. The technology itself is not anything particularly whiz-bang. It's an amine scrubbing capture technology. It's used in cleaning natural gas. It's used in a lot of places, and it's just never really been applied at this scale for CCS. So we think with the EOR capability, and this dovetails a lot with a bunch of the other conversations here about the ongoing role of petroleum and the growing platform that North America has as a petroleum producer, we got a lot of fields that are ripe for tertiary or CO2-based recovery. So there's just this huge opportunity. And what we really get excited about in terms of scalability, so you go back to the 100-fold drop in solar prices, the threefold drop in gas prices. All these things have to do with scaling up, learning by doing, getting economies of scale, getting folks competing with each other in solar, in fracking technology, and we think exactly the same thing will happen in CCS technologies if this EOR sort of, instead of waiting for a $90 price on carbon, let's just go get the oil that's out there. Typically, this is inframarginal oil, so it doesn't add any CO2 emissions. It's, it just changes like where it's coming from. It doesn't cause more to be burned, and it's coming from the U.S. And so we think that's just a highly scalable thing. There are some of the, loan guarantees, cost sharing, early serial number risks that need to be addressed through appropriate policies. And we have some great DOE support on this project, but we do think it's scalable, and we do think it's a great way to get the post-combustion capture CCS down this cost curve to where it actually can become globally deployable without a magical thinking about prices on carbon.
Well, great. Okay, well, thank you. That was a wonderful explanation. Dan, I want to turn to you, and actually, this will be a question for all of you, and then I'll sort through these questions. But so basically, the U.S. EPA has proposed a clean power plan for the U.S. that's focused primarily on reducing greenhouse gases to 30% lower than 2010 by 2030. And can we do this? Do we have the technology? And if we don't have the technology, what do we need to do? And can we get it in time to meet this requirement? And really, this is for all of you, but maybe Dan could start off with that.
Yeah, well, I just got a letter from, I don't know, I think it was at least a half a dozen senators asking myself and Paul Alivisatos, who's the director at LBL, at Lawrence Berkeley Lab, a little bit of the same question. What's the best techno-economic analysis that we have today that can really focus on is some of the projections in terms of the power plant rule achievable? So we will respond, and we'll do that in a very disciplined sort of way. There's lots of studies that would suggest that with certain levels of assumptions that the cost parameters that have been used by some who are suggesting that it may not be feasible are a bit, they don't fully accommodate both the drop in prices and the further expected drops in prices that we can have in the future for some of the alternative or competitive technologies that allow us to achieve the requirements of that rule. So without getting into the politics of the rule itself, I think there's certainly I think a rich debate, and I believe there's an answer to the question that would suggest that we can do a lot toward getting there than people think, a lot more to get there than people think.
What do the rest of you think?
So let me step back for a moment from the Section 111D and other things, and let me just address how big the carbon problem is. So today we are emitting about 10 gigatons of carbon and appropriately 34 gigatons of carbon dioxide per year globally. And that rate is going up. And so if the CO2 molecules in the atmosphere essentially stay there for a long time, hundreds of years. So what we're doing is that if the rate is going up linearly, we are accumulating in an exponential quadratic way. That's what's going on. So all that we're trying to do in trying to integrate renewables, et cetera, is trying to get the rate to be, trying to get it flat globally. If you get it flat, the atmospheric CO2 still goes up linearly. So we need to get it this way if you really want to address the carbon problem. And coming back to the CO2, we don't have a carbon price, and I don't know when we're going to get one. But we got to get to action right away. And the only way to do it is exactly what you said, is to find value. Now, the carbon scale is so big that of the 10 gigatons, you know how much plastic we made out of carbon? We use about less than 1 gigaton of carbon for all the plastics made in the world. So the only thing that scales in the world for carbon to be used in some way is fuel. And what is really exciting about the 2 cents, I think Ahmad this morning, and he's going to talk about it more, about 2 cents a kilowatt hour in electricity is, if you want to do something with the carbon to make a fuel, the cost of carbon really doesn't matter. It could be $500 a ton, but it's the cost of energy. And when you talk about 2 cents a kilowatt hour of energy cost or electricity cost, you can actually make fuel out of the carbon. And that is a very different ballgame. And I hope that's where we go eventually, so that we actually come full circle in the carbon cycle without waiting for a carbon price.
You go ahead.
Let me add a little bit on the 2030. First of all, we probably can't meet the 2020 targets because of the time it takes to do the fuel change. In PJM, we will have shuttered by May of this year 26,000 megawatts of coal. We've cleared 35,000 megawatts of new iron on the ground and about 10,000 megawatts of new demand-side management. We can make this transition, but 2020 is going to be a very tough time because of the amount of time and capital it takes to make the conversion. We can make the 2030 with the use of natural gas, and it's happening automatically because gas is efficient, 60% efficient, and gas is low cost. We need to look at combined heat and power because that's 80% efficient and can work with microgrids. But to his point on carbon capture, the 2050 target cannot be met with gas as the transition fuel. We have to be able to capture carbon from a combined cycle plant, not from a coal plant, in order to meet those 2050 goals.
Yeah. So that's great that I waited for you to say that, because our view of the 2030 goals is they are achievable. But there's two things. First, that we agree the 2020 goals in the proposed rule are not achievable, and if they were achieved, they would involve building a really massive amount of new high-capacity factor natural gas that over its life would probably emit well over half of what would be avoided by shutting down the coal plants an extra, in that first year instead of stretching it over just 5 more years. So that doesn't really compute. But the important thing is, I think I agree with both these gentlemen, is it's 2030 is incredibly important in terms of turning the corner or flattening it out. But to really do anything about climate change, so if the blanket's too thick and you're roasting in bed, you can't just stop making it thicker. You actually have to get the blanket off of you. And so the 2050, 2060, 2070 goals, where we really, according to the best science, we really have to basically find a way to do almost everything we do with no net carbon increases by then, is really important. And that one of the things that means is that the role of natural gas in the power sector is going to be really important, but it's going to be increasingly important to have it, in our view, stitch together those moments when the sun goes down and everybody gets home and turns on all their stuff. Even though they have smart gizmos in their home, they still turn on their stuff because they got home. And there's, the power is falling and the consumption's going up, and all the batteries are already drained out, and there needs to be some gas probably for a while. But we've done some estimation that the amount of gas that would be needed in a gas plus renewable plus smart efficiency sort of world to replace the 49 or so gigawatts of coal that would be retired, if it was done in combination with all these other renewable and smart technologies, would emit between 2020 and 2050 would emit less than 500 million tons of CO2. Whereas if you replaced it all with just natural gas combined cycles, it would emit about 1.7 billion tons. So, we really need to get beyond reliance on natural gas to using it as a way to facilitate these cleaner technologies and more innovative technologies and business models. And we need to do that. We can't stop in 2030, and we can't lock in the wrong stuff by 2030. We got to use the 2020 to 2030 timeframe to figure out how to go further than 30% and make money and create value doing it.
Well, that's great. That was a wonderful discussion. Okay, these are questions from the audience. I got a lot of really great ones, so I'm going to combine 3 of them, and I'm going to ask you to, when you listen to it, think technology. Don't think policy and markets, okay? Okay, so they're kind of the same question. So the first one says, with Apple and Google building out their own renewable energy systems, what's the probability they will become the new utility providers in the future. So, and then a related one is, how should electric utilities embrace solar instead of fighting it? What should the new model be? And the third, again, related to that, where do you see the future utility business model in 5 and 10, 25 years? But again, if you could talk about technology, not the finance and so forth.
Maybe I'll take a crack at that since I spend every day working on all of those issues. The key thing I think here goes back to what I said about these technologies being very disruptive to existing business models, not just the regulated utility, but the whole way we build and operate power plants, the whole way we monetize our distribution and systems and stuff. So it seems to me the key to the future is saying, look, we continue to need connectivity, to make this multiple value proposition that I talked about. We need to be able to sell to Terry's system and to utility system and to customers. And customers can get more value if there's some kind of connectivity. The way we pay for that connectivity may have to change. And the amount of it that we need may have to change. But where there's common property, common public convenience sort of things, whether it's utilities or roads or airports, we use those in our society. So we have to find ways to support them and to help make them more efficient and to help make their capital investments attractive and sustainable. Stuff like the REV process in New York. I'm trying to point to Richard Kaufman out there wherever he is. There's a lot of great ideas going on about how to integrate these things as opposed to saying, utilities should fight distributed resources and distributed resource providers should fight utilities. So I think that's a big part of it, is figuring out how do we attract capital for what needs to be regulated, and how do we let the competitive market attract capital for stuff that's available for sale down at Lowe's and Home Depot, and how do we make those two things shake hands in the middle and create value? So let's...
Yes,
Two
okay.
things. All right, so I will just a couple of sound bites. So first is measurements, sensing, control, data analytics, and that will unleash the opportunity for consumers to actually build new products, services, and new functionality, which we've never had before. And so commodities, electrons are commodities, and it's energy services that will ultimately guide. Technology will enable that. I think it's a really, really stimulating, promising world ahead of us.
And I think that's central to what I was talking about. Otherwise, it's just words.
And I think that's the last word. So thank you all very much. Yeah.